Hello, everyone, and welcome to this week's Crunch seminar. So we have two talks for today. Our first talk would be by Dr. Giselle Fernandez. She would be talking about predicting wind-driven spatial deposition through deep autoencoders in a complex terrain. A little bit about her. She is a simulation data scientist for the above and the below ground physics in the atmospheric science research and the application group laboratory at the Lawrence Livermore National Lab. Her current work focuses on machine learning and uncertainty quantification approaches applied to atmospheric flow, transport, and hazard assessments. She received her PhD in aerospace engineering from the University of Florida in 2018. With that, let's welcome her for her presentation. You may want to start Giselle.
Thank you, Somdata, for the presentation. And I was saying to George, thank you for the invitation. It's an honor for me to be here. This is work that it has been done with team members, and it's great to work in the National Lab because you had the chance to work in multiple problems, amazing, unique problems. However, it's hard to leave the programmatic side of the work to focus on research and publication. So I hope you guys like it, and I hope you can. This is work in progress, so I think both of us will learn today, both sides. And some data, one question before starting. How much time do you have for the presentation?
It's 1 hour.
Okay, perfect. Yeah, that's what I thought. Okay, let's start. Okay, first of all, I want to introduce the team. So at Livermore, we work in multiple teams, but the work I'm presenting here comes mainly from these amazing people. So Wai Tong, it's my current summer student. He is a PhD candidate at Stanford, and he's currently developing a three-dimensional temporal prediction for plumes transport into the atmosphere. It's a very challenging problem, and he has been great. Like summer students have only 3 months to work, so has been doing great. Yinan, he's in RPI right now as an assistant professor, but he was my student last summer, and he developed a spatial temporal prediction as well, but it was based on binary data, and it was two-dimensional, and he actually created an architecture for it, and he was able in 3 months to publish a paper, so that was pretty amazing as well. And Don is the principal investigator. He helps a lot. He has always like great ideas, and he is helping supporting the team. He funds a big portion of it. And in case people is interested to download these publications and possibly other publications, so you can follow the link. I don't have this particular presentation yet there, but I will do it at some point today, so you are free to go there. And well, I'll let you start with a motivation for my work. So I don't think this model needs introduction. So this is like the conventional way how we do things, right? Like we observe a phenomena, we have equations that models the phenomena, and these equations have assumptions. Usually we simplify things, and when we are ready, we discretize the equations, and then we use grid to characterize the domain, and then through input files, we like give the parameters that we wanna describe in the phenomena we wanna solve. Then we send it to the supercomputers and we get simulations out of it. We get predictions. These models has been working great for a long time. And so we don't intend to change any of this. But maybe focusing on the, how you say, the, I don't know if flaws, but what's missing, right? Like, for example, due to that there is some simplifications, it could be there like some physics missing. For example, turbulence has been a big deal for a long time, and there are ways of modeling, but it's still a challenge. So things like this, we wonder if we can get more insight to it. And so we came up with an idea, and it says like, well, what if we could just like learn from the real world itself, and collect images through cameras, maybe lidars. Are a new thing to me. I didn't know about them, but what they do is like they scan the world, right? And they get information about elevation of buildings, elevation of geographical features like mountains, and it gives, it can provide that information in a way that a machine learning algorithm can process it, and it's really cool. Okay, so we the intent is to collect information from the world, and then through machine learning, allow the machine to learn from it, and predict and make predictions, and because it's based on real images, it will be predictions of the real world. And so and we hope that this gives some insight into the physics. By the way, I forgot to say it at the beginning of the talk. Please, if you have questions, you can unmute and ask, or place it your question in the chat. I'm really bad like catching questions in the chat, so some data, if you can let me know if someone has a question, it would
Yes,
be great.
I'll let you know.
Okay, so this is an example of some great technology, like that it's available to us nowadays. For example, this is called NERF, and what basically does, I don't want to get into details because actually this is something that we're planning to leverage in our work, but we didn't develop. This was developed by Mildenhall in 2020, and then recently came out a paper that NVIDIA, the company, has used this NERF, and they have improved it using multi-resolution hashing coding. And it looks very promising because it can be done almost in real time. And what they do is, so you get some pictures from the real world in different, from different perspectives of an object. And this can give you a volumetric representation that it will look like this. And well, it can have like multiple applications, but for the purposes that we are interested, this can be like an example of a technology that it's out there nowadays. So that's why also we feel that this is a good time to try out the approach. And now I want to mention what are we gonna refer with learning from the real work in this preliminary work, because even though I give like this like a very how you say this ambitious motivation, we're not there yet. So what we did is okay, we had some simulations, and we have simulation data, but we said, okay, let's train our machine learning models using RGB values instead of physical quantities. So we can then move to real world images, and this is what you will see later in this presentation. So what we did is we just pick a color map, and this color map has different intensities. Each color has different intensities. And what we do is, well, we map it with this quantity of interest. In this case, this is deposition. Of course, it will be almost impossible to get deposition from an image, right? But it has it was handy for us to take deposition because it's easy to get from simulation. You don't need to run it a very long time, and it has resemble of the real plume, and so that was the motivation of why we're actually getting deposition. But of course, from an image, we won't get that. We will see the concentration maybe, or like the location of the plume. In any case, we assign a color map to the plume, and we use the RGB values, and this. But in any case, it's not. You can change the color bar, the color map. You can make it a mapping and change the color map. So.
Giselle, I have a question on the. So on the right, we see the deposition of what? Is it particles? Is it what is that is deposited?
Yeah, that's a good question. Yeah, this is like, it's a complex phenomenon. It has like a small and large particles. So that's the deposition of the combination of the two. Yeah, let's say it's a gas that well, it's a gas and particle combination that it was released in an urban area. This is for an urban area, and that's the deposition of the particles. Yeah,
of any size that is in the atmosphere, deposited by the wind.
Exactly. Well, for this particular simulation, they're like I think they follow. I'm not 100% sure, but I think like they're like particles that are considered small and particles that are considered large. I don't know if the radius of the particles, these are Lagrangian particles. I don't know if they're fixed or like they follow the distribution of large particles, distribution of small particles. But I know that they are divided in two categories.
But it's real particles, right? It's a real experiment. It's not simulated data.
Exactly, it is simulated data. That's
it is simulated data. That's why you say Lagrangian, okay? Because real data would not know what Lagrangian is, but simulated data would.
Exactly.
Okay.
That's exactly right. Yeah, and that's what I was saying. Like, we want to go out there, take videos and simulate, but we are not there yet. Hopefully this year we'll get funding for actually going and doing that. But for now, we just work with simulations. So what you will see in this presentation is on simulations.
Okay, thanks.
Okay, no problem. And yeah, and we recently sent this paper and to Nature Scientific Reports, and it's being under review right now. And this is what it will be the first part of my talk. The second part has to do with the work of Yinan and Waitong, my students, and I hope I can arrive there. So let's let's start. So are we there yet? As I was saying, we're not, but the work is in progress. So let's see if I can explain what we have been doing. So these are real world spatial patterns. So this kind of images we are interested in. Of course, it's like challenging to obtain these images, but something that we saw in this from the images is that plumes, different scales, like share similarities, and that could be that it's like something that we can leverage. And here, what you're seeing are different phenomena. For example, let's see if I have a laser. Yeah. Okay. This is from a volcano. This is sand. This is a sandstorm explosion, and then fire. Right. So, but they kind of follow a certain the physics. It's similar, and the transfer depend on the atmospheric conditions, and that's encouraging. And okay, so let's go back to what we have. So in the first model, we are going to predict a steady state spatial patterns. And what does it mean? Does it mean that we're not going to predict temporal predictions? So what I'm showing here is the coloring of that I talked before, and it's describing deposition. We here place more information. For example, the inputs of our model are the source location, which it's where you see more red, and then the wind velocity. It's also a boundary condition, which it will, in this case, like it's like the direction is here, and it has a certain speed as well. So basically, there are 4 scalars. And then the prediction that we want to get out of it is a colored image, but it's a high resolution colored image. So we have 3 million pixels. So it will be 3 channels for the colors, and then it's a 1000 times 1000 resolution size. And as I was mentioned, I was telling George, this is coming from simulations, and in particular, we are using ELUS, which is a code that was developed at Lawrence Livermore National Lab. So I'm just like publicizing it. Okay, so because the model we created is highly dependent on autoencoder. It's called, like I call it a autoencoder based model. Well, it's important to go through the concept of an autoencoder. This is what the autoencoder looks like. So we have an image, right, and then we encode it, and then we have a lower dimensional representation, and we decode it, right? And then it's an identity function. And there are many applications to that, and I will go into some of them in the following slide. But I wanted to show this, so we start having that representation in mind. And so this is what I was talking about. Like Autoencoder has different applications. So we have an initial image, and then the Autoencoder, the most common use is to extract the features, right? If you're, for example, for those who are very familiar with PCA, principal component analysis, It's basically that. Actually, autoencoders can be reduced in their simplified way, can be reduced to a PCA. And what it does is they extract the main characteristic or the main features, and then they are able to recover something, right? We have some flexibility here. And then, for example, one of the uses, it could be a minionization, which is currently on vogue, but there are many uses, like not as useful as this one, but many uses. As I was saying before, they're like the most common one is the identity function. So, and why do we want to do that? Why we need something that gives you the same thing, right? Can we just use the same thing? The thing to begin with, that we began with. And actually, managing the encoded information, it's easier and it's cheaper. And if someone has the decoder, you can just like share information in a reduced way. And that's what like most of like the information that is sent through cell phones works. That's the way it works, and it works great. And also the feature extraction. So if you have these images and you are able to reduce it, you can see, you can have an insight of the group of images you have. Like they can be characterized by these features. But there are other uses. For example, denoising. You have some noise, and then you denoise. In this particular autoencoders, usually you don't reduce the dimension here. Actually, the dimension is an augmented. They're called overcomplete autoencoders. And but well, nevertheless, an autoencoder. And you can also well, complete missing information from images. For example, here there are some parts that are missing, and if you have enough information about what is missing, you can train your autoencoder and to complete the missing information. And I'm sure there are more applications, but those are the one I could think of. And let's go with an example. I think to introduce autoencoders, a good example is the linear autoencoder, because it's very easy to interpret, and then it gives you insight of what actually an autoencoder is doing. So we have this very simplified architecture. Actually, real autoencoders, or the ones that are used in practice, they don't look like this, but it's a good approximation of what is the real thing. So you have here 3 layers. The first layer down here is the input layer, right? This represents like this image as an input. Then you have a hidden layer, and then you have the outputs. And then for this particular case, we are asking that P, so the number of hidden units, is smaller. So we are reducing the dimension. So smaller than N. And we are also saying that the outputs, the number of outputs is the same. The features in the output is the same as the inputs. And we have 2 matrices here. This matrix B that goes from N to P, and then a matrix A that goes to P to N. And this matrix here represents the encoder. So the encoder grabs the higher representation and goes to, well, the input and reduce it. And then the decoder part gets the reduced space and recovers the original one. And let's introduce some nomenclature here. For example, X represents a single input, right? In this case will be an image. Well, in the case I was introducing before, could be an image. Then Y will be a single output. It would be the predicted image, right? And then T, here it's the number of image you have. How large is the data set? 1,000 images, 12,000 images. And then the E is a function that is representing an error function. In this case of autoencoders, L2 norm is commonly used, but these depend on the problem and how it works best for you. And well, and then we have this represents the prediction, right? As you see, A and B are B it's the encoder, the A is the decoder, and then through this multiplication for this linear autoencoder, we will obtain a prediction. But actually, we don't know what A and B are, right? So this is actually an optimization problem, and in this particular linear autoencoder, it's very simple. It's simpler to solve, and in some cases, it also has an analytical solution. Okay, so now we will talk about the convolutional autoencoder, and I want to talk about it because first it's the one I use, and second, well, I wanted to share how actually convolutions are used in these autoencoders, right? So first of all, the reals, the autoencoders used in practice usually, well, the inputs dimension not necessary need to be the same as the output dimension. Then the hidden layers doesn't need, well, it's not one, and there are many. And then it can have each a different dimension. Also, we have many options. We have, like, when P is smaller than N, we have the undercomplete autoencoders, but then we have, if P is larger than N, so the dimension of the bottleneck is larger, we have overcomplete, and so it's more complex. And then, well, this is a mathematical definition of what a convolution looks like. This is a one-dimensional one. And we're actually, for a particular case of images, we use a two-dimensional representation of convolution. And this is the continuous version of it, right? If we have two variables. But we are not in the continuous space, so we need some discretization. And so this is what it looked like, convolution discretized, right? And let's introduce some nomenclature again. So in this case, for convolutional autoencoders, we have the first part, which is a filter, right? And then we have the image. And the filter is applied to the image, and it goes through the entire image in a step. So that's why the zoom, well, this is for a particular pixel, right? You need to do this multiple times. And O here represents the output pixel for the position ij. So this is done many times. And in order to show this graphically, I took this simulation from Sumit Saha. He posted a great introduction to convolutional autoencoders towards data science page. And I really like these two models, like the two way of visualizing. So this larger one is showing, let's say that we have an image and we have three channels, red, green, and blue. While each has some values, and then this is the kernel that we are applying, so the filter. And it goes, what it does, depending on the size of the kernel, it goes through the image. And in this case, let's try this one. As you can see, it moves one at a time. And then in this case, the output, it's just the sum of, well, it multiplies and add it up, and then it sums all the channels. And this is the output. And convolutions are usually used for smoothing or averaging and this kind of operations that they're very good for. And yeah, that's basically the introduction. Is there any question until this point before? Now I will jump on the actual model. Okay, so autoencoder based models for plume prediction. So these are the kind of autoencoders I use for the model. This is an autocomplete, which is a denoiser. Basically, the inputs are a noisy representation of the reduced space of the main autoencoder, and then I use this autoencoder for denoising the image. And then the main autoencoder, it's like I give the output that I want to obtain, and I obtain the same output, but of course there is like an error associated with it, because when you reduce, you lose information. So they do a great job recovering, but if you're asking on top of everything, that your model is cheap enough to, for example, in this case, we're using it for running it to run in real time. Yeah, it can be challenging. And this is what it looked like, the entire model. So what we did is, so we start with 4 scalars, and we want to predict the entire plume. And the 4 scalars are the source location and the wind velocity. And then in order to create this link, right, the first link is done with like a fully connected neural network. And it does a great job, right? So you might ask, well, why you didn't reduce you didn't reduce it to 4 scalars, the autoencoder. Well, usually convolutional autoencoders work great in images, but the performance is not great for scalars like in physical values. So we found a way better performance. We fully connected neural network, and this can be done because we are working in a reduced space. Imagine a fully connected neural network in the 3 million pixels domain. It would be possible. And then we grab this bottleneck model output, and then ideally we wanted to give it to the decoder part of the main autoencoder directly, but because it was a noisy, we weren't representing very well the source, which is very important in our application. So we try a denoiser, and it works really well. So that's the reason we are using it. And well, I already went through this. And this is so you can see the performance, right? Like in a qualitative way. This is the input, right? It's represented by a cross where the source location is. And then the arrow represents the wind. So the direction of the arrow represents the direction of the wind. And then the model, the speed is represented by how large the arrow is. And then the first fully connected autoencoder, the first fully connected model, which is a dense neural network, gives this prediction, right? Given this, gives a prediction, which, yeah, it's kind of expected. It's in the direction of the wind, but it's blurry. And if we give this directly to the decoder, it won't do a great job. So we we go and denoise it with the overcomplete autoencoder. And then notice that we use the entire autoencoder in that case. So we put this image and it gives this image. However, in this part, we are giving only the reduced space image, and we are obtaining the full resolution plume. And this is ground truth. So you compare the prediction with the ground truth. I selected this randomly. And let's talk about performance, because what I was mentioning before, this is, you can make this model very expensive if you want, and you will have like more fidelity, but we needed this model to perform before in less than 0.5 seconds. So, and as you can see, it's a combination of models, and we obtained this prediction in 0.2 seconds, which it's very good, and that, but you need to sacrifice like the number of hyperparameters and neurons. It's smaller, but nevertheless, it's doing as good as we need. So that's one thing.
Giselle, can you be a little specific, because the letters are small, so we cannot really see. Can you tell us what you're plotting?
Yeah, perfect. So in the lower part, I'm plotting times, right? So the histogram shows different runs of time. So I assess the model, the different models. This is the fully connected model that I talk about, that it links the four scalars with the reduced space. It's extremely fast. No, sorry, that one is the middle one. This is the bottleneck model. This is very fast. So we are talking about 0.0002 seconds, basically. And this is, the model just was run multiple times with different inputs. And this is is showing the distribution of the time that it took to predict. And the mean is in orange. And here, something that I want to say about the denoiser. The denoiser is huge. It has like a lot of parameters. However, it's very fast because it's working on a reduced space. It's working on, in this case, is 625 pixels. So that's why it's 0.01 seconds, right? In this case, the main autoencoder, which is this last plot, it takes 0.2 seconds, but because it need to work on this like huge resolution image, so that's costly. Well, nevertheless, it's good. It's like 0.2 seconds, and again, this is an histogram of the times that it took to run the model. And this is the lower row. The upper row is two performance metrics. The first one is the normalized root mean square error. And this metric takes into account the entire image, all pixels, and is commonly used on visual, when you work with images. This is a common metric. And here we have in cyan our model. This is the model that I represent. So it has the mean of 7%. And then we have a baseline. The baseline in this case is a KNN approach. What it does is search in the input data the closest input to the test inputs that I'm requesting, and it gives that as an answer. And so that model has around 13% of error. And then we have a reference model, which is just picking a random plume. And this has a 20% error. And you might ask, well, like if I'm picking a random plume, why it's only 20%? Okay, so the particular data set we work on, it's has a lot of white pixels. So each image has a lot of white pixel, and only the plume is roughly like 20 to 30% of the space. So the white will make an overlap, a good overlap. It will say to the model, you're doing good. So this is actually what we need to compare with this like 20% error. And the second plot is a metric that is commonly used on these atmospheric science patterns that we saw, like plumes, because it will focus only on the plume. We won't have this problem of it's doing great because it's like matching the white pixel. So this is also called the Jacker index, or intersection over union. And what it will see is the overlap of the plume. And we can see here that for the reference model, well, it does a terrible job. And then, well, the baseline does actually not bad, but the autoencoder performed very well. And we are talking about a good enough result here. FMS is usually require more than 80%. So the fact that we have more than 90, it's encouraging. So yeah, we're currently using this. We're planning to use this model for programmatic work. So we are very excited about it. Okay. So at this point, I'm seeing the clock. How much time do I have left on that time?
You have another 15 minutes.
Okay, so what I will do is I will go, so that include questions or not?
Yes, we can have question answer. We can also have an extension after 1 hour. That's fine. You may want to continue.
Now I'll leave time for questions. I will go faster. This is the work of my students. I work with them and I know the details, but I might know how to answer some questions. So if that's the case, I will just redirect you guys to them, but I'll do my best, but I will do it in a more like higher level. So this is Yinan's work. This is, he called it two-dimensional spatial temporal predictions on binary data. Actually, that's what I call it. He didn't call it like that. But I thought about calling it like that because it's easier to understand what he did. Like he got the data and he, so as I was mentioning before, this data is on a city, so you have buildings. And then he just processes in a way that, okay, where I have plume, it will be white, and where I don't, it will be black. So that's the kind of data we are dealing with here. And then he okay, he's doing like a spatial temporal architectures, and as you know, like LSTMs are like very good in this kind of predicting in this kind of problem situations. But he actually took a regular LSTM, and he also added wind direction and wind speed as part of each snapshot information. So he doesn't only provide the frame, he also provides information about the wind. And on top of that, he enforced first order and second order information. So he is given a little more information about like closed time steps, and that proved to improve performance substantially from a regular LSTM. And this is the architecture. I definitely won't go into details, but at the end I have the reference. You can go and check it by yourself. But basically, the main thing that differentiates this approach with like a regular LSTM is he is giving information from the two past time steps, and that is what is making the difference. And this is a nice way of showing this kind of results. So as so here you see the input data. So we have or characteristic of the data. We have 5 different speeds. So these are the challenge that the network has, like, and only have 5 initial, the input is 5 time steps, which represent 3 minutes. And and here we have different orientation as well. We have here, see, like 270 is like horizontal, and then it goes 360, which is vertical, and we have many things in the middle. We didn't have many data, so that's why this performance is great for this data. We have only 50 different cases, so actually this model is working very well. And you see here, this is the input. So the input is the first 3 minutes, and what the model is doing is predicting the last 9 minutes, and this is the truth, right? And this is the prediction, which is not perfect, but it's very closely related with it's very close to the actual truth. So this is great. And yeah, here is the reference I talk about. And let's see if we go. Okay, and this is what we are working right now. So this is a very challenging problem. I say it again. So we have 3 dimensions, a spatial dimension, and then we want to also predict the temporal component. And on top of that, it's in mass concentration. It's not binary data anymore. So it's a lot. We at the time that we got these predictions, we only did it in in 5 data sets, in 5 different simulations. But now we just run like 100 of them, so we are excited about that. But what I will show here is just with a few amount of data, and this is the architecture. Basically, it's like we have the field at time t, and then we're using like autoencoders here to predict a t plus delta t, right? So and let's see, and this is what predictions look like. So this is a slice of the simulation. Remember, it's 3-dimensional, so we have x, y, and then we have the slide at z equal 190, and then the coloring represents the log of concentration of the release of this gas. We actually we have a release that is a gas that is releasing in a complex terrain. So we have like mountains and valleys. Excuse me. And this is what it looks, the machine learning prediction. And I must say, this is very good. You know why? Because, well, first of all, we only have 5 cases. Second, we like Whitehall only train until 50 minutes. This is extrapolation. So yeah, it's not perfect, but we're extrapolating here. So I was very impressed by the performance, and this is what it will be. He will be working now. how we impose. We do like this physics informed machine learning. So we are trying to impose this the boundary condition of the terrain. And he will be trying these two approaches. One is just telling the model like, okay, this is the information, but then we have a terrain. So this information is not relevant anymore, because if we have a mountain there, the gas cannot pass through it. So that's a way of doing it. And if not, it's another way of doing it is like included when we have this like reduced space as a part of the reduced space information. So I don't have the results, but it looks promising. Well, this is a broad summary. We use physics-based simulation to train complex learning models. Our future goal is to develop an image-based models. So hopefully it will be predictive and we will compare with simulation-based ones. So the main motivation is to accelerate these plume predictions because they're very, very expensive. And also, if we get the chance to use like real world images, we will be doing less assumptions. We will do other kind of assumptions, but not the same. And we can potentially find key missing pieces in current physics models, but we don't know yet. And thank you so much.
Thank you, Giselle.
From that, I think there's questions in the chat. Maybe you can read them for Giselle.
That would be great.
George, I can't see any questions. You could see them?
Chat. Oh,
Yeah.
I don't.
Says, what is the color intensity graph for? Particle colors. I think that was the original image that you showed. This is from Rohan. Maybe Rohan can ask direct the question.
Sorry, I don't see any questions. I know something is wrong with my Zoom.
Or maybe he sent it to George directly. I don't see the question either.
Okay, so Rohan, can you ask the question? I see the question, yeah.
Hi. So yeah, I did send the question directly to George, and my question was basically about this particular graph on the bottom left. The color intensity that you are measuring over here, is that for the particles?
Yeah, actually, the color intensity is for deposition. Deposition is a quantity that is mass over area, and yeah, it represents the particles that they were in a plume at some point, but now they are on the ground.
Yeah.
Okay.
Does it answer the question?
Yeah, thank you.
Vivek, is
Yes.
Vivek online?
Yes, I have a question.
Yeah. Identify yourself and so
Yes.
that.
Yes, I'm Vivek and I'm a PhD student in Brown University. I'm working with Professor George Karnidakis. So I have a question regarding the autoencoder based model. So can you go to the slide where you showed the bottleneck model and the corrector model?
Okay, here it is.
Yes, so I want to know how you are, so if I understand correctly, you first break down the space using the autoencoder, and in the latent space, you are training the bottleneck model and the corrector model.
That's exactly right.
Yep. So how are you training the, so what is the loss function, or what are you training the bottleneck model to do and the corrector model to do? Like what loss function are you using, like specifically for the bottleneck model and the corrector model?
Yeah, that's thank you for the question. So the bottleneck model, the inputs are 4 scalars that has to do with the location, the source location where the contaminant gets released, and then the wind direction and direct. And then the output, so what we are asking the bottleneck model to predict is the reduced space. So what we do is like we have this like full resolution image we apply the encoder. The encoder will give us a reduced space, and that will be the first model. The first model will map these two things. The corrector model, which is a denoiser autoencoder, will grab the reduced space, right? Like the prediction of the reduced space, which is not perfect. So we find it that it will, if we feed directly that to the autoencoder, to the decoder part, it will give us a good representation, but it wasn't good enough for our application because this source, it wouldn't be well represented. So we needed this denoiser. Well, we tried the denoiser, and then when we actually, the denoiser maps the noise image with the denoise image, and the denoise image is we decode the training data. So we have we use the autoencoder, the encoder part of the autoencoder to obtain the image that doesn't have noise because it's the actual image. But then these guys have noise because those are not they're not coming from the actual image. They come from this bottleneck model. So they are a discrepancy between the two, and we try to fix that discrepancy using the denoiser.
Sure. Thank you. My question was, so if I understand correctly, I don't understand why you need two models, because both the bottleneck model and the corrected model will be trained against the encoded representation of the final state of the plume.
So you don't understand why I need two models in the bottleneck? That's the question?
Yes, because for the bottleneck model also, you will be training the prediction of the bottleneck model against the embedding of the final state of the plume, and the corrector model also you will be training the model output with the embedding of the final state of the plume, right?
Well,
So why do you need to? Yeah, that is my question.
Maybe the answer to your question is our bottleneck model is not performing as well as we want. So it was giving, if this bottleneck model wasn't giving noisy images, we could have spent time and correct that, and maybe we will get better results, and then we will need the denoiser, right? But we try multiple things, like things are sometimes hectic, right? Like you need to deliver, so we say, okay, let's try the denoiser, and then it was working really well, and it wasn't adding time. So that's the reason behind.
Okay, thank you.
Giselle, this is a static image, right? So how would you you talked about the evolution of like you show the LSTM, you have space time, but here you only show space. So what's your big idea for time here?
Well, yeah, that's right. This is a spatial application only, right? So this does not include time. So like when we move towards like actual videos, we will be applying more like this flavor of architectures, right? Or an LSTM or an autoencoder based LSTM model. Like, well, this is not an LSTM. This is just you give the input and it predicts the output, and then this output is fed again here, and it will, right? So there are many models, but it will be a combination of these two models. That's the idea.
Right. So Vivek, who just spoke, actually, he just published a paper for the microevolution, for the evolution of microstructure, and so he was using an autoencoder just like you do, but then he was using he was training a depot net in the latent space to advance in time. So maybe Vivek. So this is a project with Sandia on the actual deposition, physical vapor deposition idea. So I think you can use a very similar. Vivek, don't you think she can use a similar?
Yes, she could definitely try using a depot net to learn the dynamics in the the latent space after compressing the space using an autoencoder and learn the dynamics just in the latent space using the DepoNet.
Yeah, so DepoNet can certainly mimic what LSTM can do, but you have more expressivity. Maybe Vivek, you can put the the paper in the chat for Giselle.
Yes,
But
sure, I'll do
think
that.
there's a great similarity here. So,
yes,
so you can take your autoencoder, especially a 3D, what you're showing now, and add to it a DepoNet, so you can actually advance in time. So you will see also how they arrange the data in snapshots, and they can do big extrapolation. That's what this. So the pattern you show is very similar to the microstructure evolution of PVD, which is pretty tricky actually, because it was generated with Memphis, the code that for phase fields.
Okay. Well, that's thank you so much, George. I will definitely take a look at the paper, and I'll contact Vivek if I have a question. But yeah, like that's exactly what I was expecting from this seminar. Great idea. So
Sandia was using LSTM before we worked with them, and so we replaced that actually with Autoencoder, exactly like you're doing basically. The denoiser, it's a good question that Vivek asked. There's many different ways to slice it, but the point is how what you're learning, and also extrapolating in time. So the idea also. So another benefit of that is that we could, of course, you cannot extrapolate forever. So we took a code, and the Memphis code, so we could do a little bit of the simulation, then a little bit of the extrapolation, and then go back and so on. So you could speed up the code itself also. That's another benefit, because you were not going to extrapolate forever. So I think you can pick up the discussion with Vivek in the offline, and so I think it's very relevant work actually.
Yes, Judge, I'll be happy to have the conversation.
Great. Okay, well, thank you so much.
And the Sandia scientist is Remy Denenville, who is working with us. Is actually a sponsor work that we have with them.
Okay. I don't know Remy, but I will take notes.
Thank you, Giselle. Do we have more questions for the speaker?
You can always send an email if you have a question offline. I'll put it here one more time. It's Fernandez48, and I will happy to take questions.
Great. Thank you very much, Giselle. Thanks for taking the time, and good to see you again.
Yeah, nice to see you.
Let's move on to our second talk. So our second speaker is Dr. Ehsan Haghighat. Maybe you would want to share your screen when I introduce you to the team. Yeah. So he would be talking to us about physics-informed neural network forward and inverse modeling of multiphase poromechanics using stress-split sequential training. Dr. Ehsan is a research scientist at Carbon, working on challenging problems of modeling 3D printed lattice structures. Previously, he has held multiple positions in the industry and in academia, including data scientist at Geotab, postdoctoral fellow at UBC, postdoctoral associate at the MIT, and the lead mechanics developer at Hexagon AB. He received his PhD from McMaster University, Canada, and specializing in computational mechanics. His research interests include computational methods for mechanics of solids and porous media, stochastic modeling and uncertainty quantification for engineering systems, and machine learning applications in engineering analysis. With that, let's welcome him. You may want to take the floor.
Thank you very much, Samlata, and thank you, Professor Haghighat, for this opportunity to present our work. My name is Ehsan Haghighat, and currently I'm a research scientist at Carbon, and this work is in collaboration with Daniel Amini. I think I asked him to join the call, who is a prospective student at MIT, soon joined CE department, and then Professor Juanes from the CE department, and also its department. And the motivation for our work started a few years back. So I was a postdoc around 2017 and started taking some courses on, my background was computational mechanics, so I started taking some courses on machine learning and started exploring the ideas. And in 2017, 2018, a lot of papers was focused on when we generate data for simulation, using simulation engines, and then replace those data with a surrogate model like a neural network or CNN type network. Or if there is experimental data, how we can represent it, or if there is earthquake seismicity data, how we can classify it as earthquake and so on. And the same time, a set of works came, including this very well-known work by Professor Haghighat, now Professor Aisi and Professor Perdikaris, and also other works on identifying PDEs or solving PDEs using neural networks. And that was the focus of us since end of 2018. And the interest is that in most engineering applications, data is very sparse, very limited. So we would like to augment this with physics, and that's been our main focus so far. A review of some of the problems we have looked at. We actually started with a relatively complex problem in the beginning, but then we found very challenges to use no data or to use inversion. So therefore, reduce the problem to essentially elasticity and elasticity to be able to understand the approach better and to find where we can improve. And the first work was on elasticity, and elasticity in particular, what we did back in 2019 was to set it up as a surrogate model so that we can capture deformation or stresses as a function of not only a space, but also as a function of material parameters. And then, of course, now you can do it better with DeepNet and other approaches, but that was interesting work, which you would be able to have a essentially parameter dependent, like analytical solution, and would be very useful for inversion using very minimal data, like 9 data points, and the rest are just sampling. Another work we did, follow up of this one, we found that when we are training PINNs, it's very difficult to capture sharp gradients around the point of loading. And this is important for geotechnical applications because when we are evaluating stability of structures, we want to know where the failure zone is. And what we used was the peridynamic differential operator. So essentially, instead of just defining a local function, we would also take neighborhood information, and using peridynamic differential operator, we can evaluate, which is essentially like a moving average. You can think about it that way, but it also gives you flexibility to also take derivatives, evaluate derivatives, and so on. And for example, what we found was at the time, with the technology of PINN at the time, so without adaptive weights, or adaptive sampling, if you would train it with PINN, it misses one of the characteristic parameters because the plasticity zone is so narrow, whereas with PDDO, because always you're looking at a neighborhood, it would capture it. But I think it has more applications recently. This is
Ehsan, this is kind of interesting idea. So because I'm interested in non-local operators. So you're basically suggesting that going to non-local operators with a finite radius, right, with a horizon, for example, instead of there's a fractional will be like infinite horizon, but with finite horizon, helps you to identify singularities. It helps you to it helps PINNs in general to converge, right?
Exactly, that's what we found. So PDDO, pre-dynamic differential operator, is flexible to pick any horizon size. But of course, like the PD itself that we are looking, its elasticity, so the PD itself for us was local. But PDDO is essentially a flexible way to pick any horizon size. And what we found, even with a small horizon size, as soon as neighborhood information is there, there is a more chance to kind of have this error in the samples, in the batch size, and there is better chance of achieving higher accuracy with PINNs. Yeah.
That's a great idea.
Can I ask you a question though? So this is a collocation residual for the PDE, right?
Yeah.
How is the point singularity co-located with a data location? Like, is this just a question like you need to regularize the point source so that you get a couple collocation points inside the support of the paradigmatic kernel? Do you know what I mean?
I'm not following the question. Let me just. Oh, I'm hearing my. Maybe. Yeah, let me just describe the PINN, for example. So for PINN, you're sampling the loss at single points, right? And then you're optimizing for the average. And you would sample at different points, and the chance that every batch kind of hits these very narrow bands of singularity, or I don't know, sharp gradient or plasticity in this case, is much smaller, and we are always optimizing the average. So most of the solution is perfect already, but this very narrow band most likely will be missed. But with the PDDO, because you're always evaluating almost like a filter size, so there is a neighborhood information that is moving, and there is much higher chance that you always hit also these points, because you're always, if you use for example, filter of 5 by 5, you would be able to sample it much more often. An optimizer sees that information and move faster to the right direction. I suppose if we also wait for PINN for much longer time and increase the batch size to much larger sizes, we would be able to also capture that. But we wanted to keep the training time and epoch size and everything almost the same for these two approaches to have a fair comparison. Does that answer your question?
Yeah, thanks.
Yeah. So this is even more interesting for discrete
Let me
networks.
just, can I ask one, because I think Romulo is listening, and also Lulu did some work on adaptive sampling recently. So they found that basically some selective refinement with Monte Carlo sampling, a combination. So I think you enhance, I think like your interpretation, I agree with your interpretation, you enhance the sampling because that's what we've seen when we do what we call RAR, the residual adaptive refinement plus Monte Carlo sampling. So you expanded to a non-local sampling around the points of interest. So I kind of agree with you on that.
Yeah, one other approach we never published, it was a similar idea that, if I understood the point correctly, if you have a very dense sample, but if you just define a kind of probability distribution, like the work, I think Mohammed Amin from now he works at NVIDIA did for importance sampling. So if you have a very dense sample and then we find a probability distribution which is based on error, but the thing is PDE might be satisfied already. And that's the problem. And we want to make sure that we are capturing these narrow bands, which are very narrow. But having a larger kind of filter instead of just single points would help to capture or hit these points more often during sampling. And so one application that we are looking at now, actually, this is a completed work. We are very soon gonna archive it, is when we go to discrete networks like CNNs, now, so classically like discretization net from ANSYS or some other papers by Ehsan and others, and they use finite difference approaches to kind of evaluate PD residuals, if you want to go physics informed, what I mean. But with peridynamic differential operator, now you have this flexibility to essentially pick any filter size, to go to any derivative you like. And it can be easily applied to this. And what we are doing here, it's a combination of the approach that Ehsan group proposed, Ehsan's group proposed, one in FISCRNet, I think it's the name of the network. But then you would have the flexibility also to do something in the latent space, because we can think about latent space as a, I don't know, a coarser mesh, right? Some physical quantities, if we impose them to be valid at different scales, we might be able to improve the results. But this is going to be coming out soon, so I don't spend more time on it. The only point is that peridynamic differential operator gives you that flexibility to also have to work with discrete networks. So the same time that I was working, of course, like many other people, I started looking at Maziar's code and expanding a little bit on it. But then I found that I have to implement many things, and Keras already has, for example, saving weights and so on. So I started implementing our code in Cyan, in Keras, and then gradually, as a way to collaborate with other collaborators, made it a package. And I think we open sourced it in 2019, but it was just myself looking at the code. But gradually after, especially we archived our paper, and it was interesting, almost the same time as Lou archived the deep XCV. I was also writing that Cyan paper, but anyway, I'm happy that lots of people used it, and I think many more people use the deep XCV, and now SIMnet from NVIDIA, or Modulus, actually, they renamed it. So this is a review of our previous work. Today's topic is the use of physics-informed neural network for forward and inverse modeling of multiphase poromechanics. Actually, we started with this, but it was quite complex to train, so training didn't converge at the time. Adaptive weights were not popular or not used, or we were not aware of it. And then gradually, so we went back to elasticity, simpler problem, and came back to this later on. But still, this is like a work of last year that are being published now. A sneak peek at the sequential PINN architecture that we are using. So there are two ways to define the neural network. One is as a solution method. One is to have a single network with multiple outputs, right? And then you would do the automatic differentiation and evaluate the losses and so on. The other is to go more like a finite element setup, to have separate network for each solution variable. What do I mean by finite element setup? In finite element, or in most discretization methods, each solution variable does not share degrees of freedom, which is network parameters in neural network, with other. So every variable has its own degrees of freedom. And that's, we have explored it on different problems, but in particular, for this optimization, if you want to use operator split, if you want to use kind of sequentially train on temperature, then fluid, then solid, we only have this choice, because otherwise, if we go with the full network, we cannot freeze the output, for example, on pressure. We can't freeze, because as soon as you optimize for displacement, it's a part of the same network, you're perturbing pressure. So operator split is common, or segregated training and so on is common in classical methods. And we found that it's also very flexible and can be used here very easily. And just also a sneak peek at results that I'm going to present later, we found that using this sequential training, we can now solve coupled forward problem and also inverse problem. And the most interesting part is for the inverse, you see like the first iteration, the accuracy is low, like it's going to the right direction, but one of them is undershooting the target. The other one is kind of overshooting. And then second iteration, it gets revised and so on.
So Ehsan, it's not actually because sequential used for something different now. Sequential means like in time, but I think you're talking about splitting operator. Splitting
Yeah,
right.
Sequential optimization, sequential training. That's right.
The term is used now for more like sequential in time, like from Windows. Instead of doing one block in time, you do multiple. But you actually split the operator, and therefore you have correspondingly, you have a sequence of neural networks.
Exactly, a sequence of training. That's what we mean here. Yeah, for time also. Yeah,
but not of the same operator, because you split the operator.
Exactly.
Clearly splitting scheme.
Yeah.
Let's make a quick comment about network B. So as drawn, you can't freeze it because all 5 of the fields are sharing the same final linear layer. But you could have it so that they all share a single hidden layer, and they just have, each one would have its own final linear layer, which would allow you to freeze it.
Actually, final, you can freeze it. Final, there is no issue. The issue is the parameters before, because those are the shared parameters. The final, each variable takes its own set of parameters, right?
Nat, I think what Ehsan meant with the finite element analogy means basically a different basis or different spaces. Right? That's why you mentioned that, yeah.
Exactly. Like, sorry, I'm not a mathematician, so maybe I use more engineering kind of analogies, but yeah, that's exactly right.
Yeah, the distinction I was trying to understand is effectively, like, are you having a different mesh for each field, or is it that mechanically you need to be able to freeze each field? Like which is the thing which is giving you the benefit? You know what I mean, in network A versus network B. You're claiming that actually having different adaptive bases for each field is the desirable piece, right?
So what I mean is to this: if you sample XYT, right, pass it through this network, before the last layer, the information, essentially the information that is passed to the last layer.
Nat, can you turn off your mute your, yeah.
Yeah, I think maybe there are 2 microphones, and then that causes the issue. So when we sample this network to evaluate the losses, before the very last, so last layer is fine, because last layer there is no sharing, right? Each output takes its own parameters. But before the last layer, the parameters are shared. So any sampling of this network, you would essentially get a set of outputs for before the last layer. And that output affects every solution variable. But in a classical operator split approach, you would want to freeze, for example, temperature when you are solving for displacement or pore pressure. You want to freeze it. You want to make sure it's not changing in this period. But that's not possible with this approach, because you don't know where to freeze, because these parameters in this region before the last layer are shared among all outputs. So you're going to describe this later.
This is consistent with what we have seen recently. I have a postdoc, Simin, who is listening, and she's looking at some OD models, like neuron models, like the Huxley model and so on. And she was only able to do that with splitting, what you're showing here. because you otherwise it's like a floating all these parameters, but the
Exactly.
splitting operator. So you can basically, the splitting error is not that big compared to all these other errors that we commit in neural networks. But it does seem to. I'm looking forward to see all your results. But yeah, we do have some similar experience for OD so far.
Yeah, thanks. So I think, the error may not be as severe as the target errors that we are setting up for, but yes, it's still like in a classical sense, we cannot freeze it, and that was exactly the idea. So, but when we pick network A, now we can solve in a coupled manner, like in a simultaneous solve, or we can go sequentially. A brief description of multiphase flow in deforming porous media. So this has significant importance in engineering, so essentially in water resources, in agriculture, oil and gas, or geotechnical engineering. This is a well-known figure from California and near an agricultural field, and you see that over like 50 years of water extraction, there is a huge depletion on the surface. And for example, this cannot be captured if we don't consider the mechanical interaction between pore fluid and the soil particles. And so how this is done, this is using Biot's theory of elasticity of porous media. So the first set of equation is similar to solid mechanics, right? We have the momentum balance of the matrix with a constitutive relation that describes the relation between stress and strain or deformation. But also there is a coupling term, which is the function of pressure change, pore pressure change in the system. So now how pore pressure evolves over time. So you have the mass balance of the pore fluid. And we have the seepage velocity, which is described by Darcy's law. And once we have these and a set of constitutive relations, which shows kind of how much mass can be stored in a controlled volume, we can describe this system. Now, if this is a single phase, like fully saturated, now, if you go to multiple phase, the pressure now is average of pressure of different phases. So you have, for example, gas and water, or you have oil and gas. The mass balance is written separately for each phase, and you have the Darcy law for each phase, but then they get connected using some empirical rules, essentially capillary pressure as a function of saturation and so on. You can also have kind of heat transfer in the system, which would result in an increase in temperature would result in expansion or shrinkage of particles, which would limit how much water can be stored or how much can be extracted and flow through the system. And so, but overall, the conservation remains almost similar, except for this constitutive relation. So that's the coupling part. And now you have mass balance or mass conservation for each phase, but also now the storage capacity varies by temperature. And then you have the heat conservation, which kind of how much heat can be stored, and then how it affects how it transfers through the system. So given these governing equations, you would be able to describe, but as you can imagine, there are now so many PDEs, and each one has its own boundary conditions, Newman and Dirichlet. So there is like, even the optimization problem is itself, even if you were able to use like a couple solve, a simultaneous solve, there are so many terms that we need to solve concurrently. And as soon as we go to multiphase, now you have these empirical saturation curves that are highly nonlinear. So starting from a random state would perturb the system significantly. So that's the main challenge. I don't think I need to explain neural networks here, just for the sake of presentation. And if anyone, a student or someone is looking, I kept these slides just for flow, but really I should not talk about this. So the main neural network architecture that we use is the feed-forward densely connected neural network. You have a set of features, and you would form this affine transformation followed by a nonlinear mapping, and you would form each layer and all the way to the last layer, which you get the prediction as a function of inputs. And in a classical or most popular setup early on was the image processing setup, right? So the feature space is quite large. Each image has millions of pixels. Even the convolution has still thousands of features to pass through the network, and ultimate goal is to classify it. But interesting part for us is we want to measure the formation or stress as a function of space and time. And you can see like the feature space is very limited. And that's why as soon as we add, for example, neighborhood information or Fourier features or things of that nature, we can increase trainability of the network significantly. This has also been used for example, approximating geometry, right? If you have a sine distance function, it's just another function. So we can, and it's been quite popular recently in the computer graphics community to use such neural networks to represent geometry and scenes. And really, our motivation and our interest started from this work by this group. And the interesting part was that, so of course, there were a few papers earlier, even back 80s, to use neural networks for solving PDEs, but combination of features as a whole made this paper quite impactful in the field, which is, first of all, not using, for example, discretization methods to evaluate derivatives, just using automatic differentiation. So using it for both forward and inverse and so on made this paper extremely successful and impactful in the field. And that's the setup we also going to be focused on in this talk. So back to PINN THM and how we solved it. So the first thing is we found that if working with dimensional equations is very problematic, especially now that we have multiple PDEs. One is a kind of hysteresis are within megapascals, then you have flow that are quite slow and so on. So combination of this was convinced us that we need to switch dimensionless. And so the first step is quite simple. You just scale the parameters, both input and output, to make sure input and output to the network is take some values within -1 and 1. Doesn't have to be exactly the same, but the idea is that because network initialization is in such a way that the input that is expecting is range of 1 and output 1. So if we scale the parameters this way, we can immediately take advantage of network initialization and optimization methods that are currently used. Then for the inversion purpose, we also need parameters of the PD to look at them differently, because those are also parameters of the network. So we need to also scale parameters of the PD. So having these now, if we substitute it into the previous equations that I discussed, you would end up with such a relation for the solid phase. And the second relation, which is like mass balance, including the Darcy law for the multiphase flow in porous media, and for the heat transfer. So these are the set of equations that we're going to be using. And some characteristic parameters, they can be factored out from these equations and set by setting some of the factors to 1. You can kind of couple some of the parameters, which is basis for, I don't know, pi Buckingham theory and so on. But anyway, these are well described in our recent papers. So if someone is interested, please take a look there. But now, why this is important on the dimensionless versus kind of dimensional formulation. So for the same network, the same seed number to initialize the network, the same optimization parameters, if we use the dimensionless form, we can capture the solution much faster than if we use the original form. So you can see within the same training time, the results are not good yet. So back to operator splitting in classical kind of porous media. So you have this equation, we have this equation for solid, and then in the dimensionless form, we have this equation for the mass conservation. This is like a fully saturated case. But then volumetric stress or average stress can be now, we can express it because of the constitutive relation as a function of volumetric strain. So we can alternatively use equation 2 or 3 with equation 1 to solve the system. And in a simultaneous solve, in a classically known coupled solve, if we use 1 and 2 or 1 and 3, they are identical. So they don't change the nature of the system. Whereas if we want to do operator split, then you have two options essentially. You can freeze the stress and solve the system sequentially, or you can freeze the strain and solve the system sequentially, which is called strain split. And it was shown a while back in 2011 by, at the time, Hamdi and Ruben's student, that if you use a strain split, the kind of integration scheme, the Euler scheme, is conditionally stable, whereas a stress split is unconditionally stable. And interestingly enough, and we observed the same behavior with PINNs. So even though like there is no one-to-one correspondence between these two approaches, we observed almost around the same critical point, a strain split starts diverging, whereas a stress split doesn't care, and you can, with any parameters, you can solve the system. It may not reach the accuracy because of some other issues with optimization and neural network itself, but it doesn't diverge. So that's the idea of the operator split. So now we can set up the losses. So we have the loss for solid. This is, I simplified to 1D, but you can write it with all the dimensions. So we have the losses. It's a weighted sum of Dirichlet, Newman, if we have data, and the PDE loss. And also we can have losses for fluid and temperature. And total loss is, of course, summation of all of these terms. So I showed you this earlier. Not going to spend a lot of time on it, but the idea is we use network A, and we use a sequential training. We first solve for temperature, then freeze temperature, solve for fluid, freeze pressure and temperature, solve for solid, and go back and forth. One advantage of sequential training also for coupled problems is that we don't need to start from a random state. So if we want to solve a coupled system in this scenario, and if we have network B, the full network, what happens is that the very first iterations of gradient descent is all random. So because if in a simultaneous solve, we just put everything together, then the initial values for stress and temperature, not initial condition, the very initial values that temperature, stress, or pore pressure has, especially for the case of multiphase flow, which you have some empirical saturation dependency, it's quite chaotic now. So we found that in the case of multiphase flow, actually no luck at all to be able to train the simultaneous solver. Even in the case of single phase with deformation for a relatively simple problem, it was hard to train it. Whereas in the sequential training, we know we can, when we don't have a state yet, so when we haven't optimized anything, like any kind of classical solver, we can initialize it with 0, which is associated with the decoupled system. So it makes actually perfect sense. So then you solve for temperature, you update the temperature at grid points or at collocation points that you want to solve for pressure. You update for pressure, then you update pressure and kind of for every phase, and also temperature at collocation points that you want to solve for stress or displacement, and so on and so forth.
Ehsan, I have a question. So clearly you have now time windows, right? You have time stepping, so to speak.
No, it is every equation is solved in full time. We don't have
The full time, so you don't do okay.
Yeah, we just these are the optimization iterations. So we optimize first for temperature equation, then for
so you consider the full time. You don't do blocks of time.
No. Actually, that's a great point. We experimented. We never did it, but as soon as if you make the time block smaller, something like parallel or XPINN, which Ameya has done a lot of nice works, and others in your group. But when we make the time window smaller and smaller, these problems are less severe. But we wanted to stick to full domain, no kind of decomposition, full domain in a space and time, but be able to solve these PDs. So yeah, that's the approach that we use. And in our experience, usually 5 sequential trainings was sufficient to solve these systems. Of course, these are more or less academic problems. So our objective here is to first find a reliable solution method for PINNs, using PINNs for solving non-isothermal or THM processes in porous media. So that is our main focus, has been main focus. We don't want it to be sensitive to network initialization or, I don't know, slight changes in learning rate or things of that nature significantly affect the solution. Then we wanted to address some fundamental problems of flow in porous media. The problems I'm going to discuss are relatively simple with respect to things that we can do today with finite element or finite volume or CFD solvers. So there is not a comparison one-to-one. But these are the same problems that was used in 60s and 70s and 80s to validate or to kind of set up those solvers. So that's our objective. And we want the results to be physically accurate. Sometimes, especially in the case of multiphase flow, we see that the loss is going down. Actually, if you just look at the loss, the results are supposed to be quite accurate. But then when you look at actual results, they seem to not belong to that set of boundary conditions that we are after. And this is also makes it very challenging to kind of automatically identify whether we are solving the right system or not. So the first problem is the Mendel's.
Sorry to interrupt, Ehsan. Before you get into the results, are you writing the Darcy in mixed form? So like, do you have a neural network for the fluxes and also one for the pressure? Is that right?
For the flow, we just have for pressure. If it's a single phase, if it's a multi-phase, then we have for pressure on one phase, but saturation for the other phase. Or sorry, capillary pressure for the other phase.
I guess the question I wanted to ask is whether you run into the usual kind of INF-SUP compatibility things that people have when you worked with the mixed form of Darcy flow for finite elements.
So our flow solver is not mixed form. So we take derivative of P to evaluate velocity.
I see. Okay. All right. Great. Thank you.
But the solid part is mixed form. So we have network for displacement, but also for stresses. And then we connect them with constitutive equations. We don't do second order on the solid part.
Mm-hmm. Thanks.
Yeah. So the first problem, we looked at Terzaki and other problems before this. Those are kind of decoupled. So if you solve for pressure first and then solve for displacement, it is equivalent to solving the coupled problem. But the first full coupled problem is that we looked at was this Mendel problem, which is a simple setup, but very impactful in terms of validating numerical solvers. So And the setup is simple. You are applying a sudden load on the left edge. All faces are impervious, so we don't have flow here except from the top face. The solution envelope is like this. If permeability is very high, right, you apply a load to a highly permeable system, so water just escapes. Therefore, there is no pore pressure generation. On an extreme end, it is called the drain condition in geotechnical community, which means that these external mechanical forces don't have any effect whatsoever on the flow. On the other hand, we have a strongly coupled, means that flow cannot quickly escape the system. So you apply the force, but the force, because flow cannot go and fluid is less compressible to solid or rock, to soil particles or rock. Therefore, in the beginning, all the force goes to fluid and it cannot escape. And gradually it starts with a very low rate escaping the system, relaxes the pressure inside the fluid, and then force transfers to solid particles because the total force remains constant in this process that I described. So this is called strongly coupled, which is on the extreme end, it's called undrained condition, meaning that flow cannot escape the system at all. Therefore, all of the force usually go to fluid. And the interesting part about this, you can see, like in this case, there is not much pressure generation, only 0.1. But in this side, now we have pressure. It's a little bit small, but we have pressure that goes beyond the applied force. So we have even more pressure generated in the fluid because of the setup of the problem. And this part was extremely hard to capture, and that was the interesting of this problem. So one question was, okay, which approach we pick? Should we pick a sequential solver, a simultaneous solver? Should we do first sequential, then simultaneous? What do we do? So you can see this is the exact solution. This is the sequential training. So the rates are captured very accurately. There is a little bit of numerical diffusion. As I said, as soon as we reduce the time size, or we do it like in multiple time windows, this would go away, but we don't bother about this for now. The main part was these rates are correct and these overpressurization are more or less correct, of course, within the expectations from neural network. And that's the best solution we got, and very stable. You change the initialization, it works fine. So with the simultaneous training, and the rates are not correct, and also overpressurization was much harder to get. Still, this is a simple problem, by the way. And if we do sequential, then simultaneous, so we do like 3 sequential trainings, and then save the weights and continue with the simultaneous. And we were hoping that, okay, after 3 sequential, we are now close to optimal points. What if we just put all the PDEs there? And we found that when you do that, actually diffuse at third iteration, the result was already similar to this. But then when we put all of the PDEs together, we found that it actually perturbs the system in a way that is physically less accurate than the other one. Although, like in terms of, if you just look at the total loss value, they are all equally good. It's not obvious to decide which one is better. The second one was a stress split versus a strain split. So you can see, like in the case of a stress split, it is no matter at which DS star we are operating, that parameter that I showed earlier, that controls a strongly coupled or weakly coupled. So no matter at which DS star, first iterations the results are decoupled, right? Because there is no information passing between fluid solver and solid solver. But then second iteration, third iteration, the coupling effect comes in and you get the solution. Whereas for the strain split, it diverges. I think this is interesting kind of for people interested in analysis and classical analysis of these methods, why this happens. I had this in my to-do list for quite some time to look at it from using NTK matrix, but really with day work, it has become very difficult to focus on more fundamental problems. But I think this is a very interesting from a academic point of view to understand why we observe almost the same response compared to classical methods. One thing that we explored for almost a year, we searched for multi-objective optimization methods and anything that was applicable to PINNs. And we found that generally speaking, gradient scaling works best because these are, at least for the forward setup, certainly. We found that among them, grad norm, which is a 2018 paper, is the most interesting part for some reasons that I'm going to explain now. So it is gradient scaling. So essentially, you take the gradient of losses with loss terms with respect to parameters, and you would evaluate some norm. And you want to scale it, for example, to be to all the gradient norms to be with some average or some maximum, to be scaled according to average of all terms or to maximum of all terms or minimum. Maximum would take you to gradient pathology by Stefan and Paris and yeah, people from Paris group. But so this is grad norm has one extra component, and that is called a score. And what a score does is measures how far how good you are in the absolute loss. And this was interesting because let's say we have a multi-objective optimization, right? And in the simplest form, let's say it's quadratic. By the way, this is an analogy that I use taken from the book by Numerical Optimization by Professor Nasadol. He uses this analogy for multi-objective, and I think that's what's happening. So we have multiple objectives, right? And one of them, or let's say, is at one gradient iteration is at this point. The other one, let's say, is close to optimal point. So what gradient scaling does, right? It says that, oh, this gradient is small. Let's make it larger and larger. So what it does, it accelerates training of this loss term. So it pushes it to 0, 0, 0. But what we want is to push also this one down here, right? And other terms. So a score controls that. A score measures how close from the initial state, how close we are to, or how far we are from the initial state, assuming that all of them at the initial state take large numbers. So if you are now far from the initial state, that means we are most likely close to its optimal point. So the score for this becomes small. The gradient scaling becomes large. Multiplication of these two controls roughly to not kind of overweight this last term compared to others. And we found this approach works best for our problem. If we just use, for example, gradient pathology, either we have to use this Euler update, this beta update, either we have to use it very small so that the weights are updated very slowly. Otherwise, it quickly kind of runs into very large values for some of the terms that are converging faster. And yeah, the original author has it this way, using some gradient descent update. We followed a similar approach to gradient pathology by solving these absolute values and using some algebra and expressed it this way. So this is the gradient, the kind of adaptive weight strategy that we use in this works. And the results are here. So this is the result from gradient or using sequential training. And for sequential training, actually, most of them worked equally. We need it, but for example, because now the losses are non-dimensionalized and so on, for the Mandel problem, at least, even just having it unweighted was not that bad. NTK was always good, but it would result the computational cost is quite higher than gradient scaling, and GP, the distribution slope is not good because it balances the maximum. So you get the boundary variable, but then the error inside is a little bit higher. But essentially, grad norm is very similar to GP in principle, except that the score term, which I think is important. And with sequential, you can see NTK is good among all, but yeah, none of them are good. Simultaneous. So this is a simultaneous solve. This is a sequential solve. So now
Hey,
that
Ehsan, can I ask a question here, because I'm a little confused, and I appreciate the all the contributions, but in terms of the accuracy, are you still off by, because I look, let's say that the cyan curve, right, the T equals 500 curve for the pressure,
Yeah.
the exact pressure and the pin pressure are way off.
Yeah, this is I described this is like these curves are diffusion over time, and because we use just a single very large time step, total time is quite large, like from the very first one,
Right.
from
So
zero
this is what I was saying before, that maybe the time windows would actually give you the correct evolution.
I agree, and we actually tested that, but we never kind of published it. So if we reduce the time window to, let's say, instead of just solving for 1000 in the dimensionless form, if we solve it for 10 hundreds,
right,
it would immediately resolve
that.
this.
Okay. That's what I meant. Okay, great. Yeah, that's fine.
Yeah, because the paper was just expanding and expanding, so we didn't include that, but we tested and we validated, at least for Mandel, that exactly, for example, a time window or parareal would be a better choice in this case to resolve this time-dependent diffusion of numerical diffusion, not the physical.
Sure.
Yeah. So the second problem that we looked at was Barry Mercer. This is also a very classical problem in this community. I realize we are, I think, at a time almost. I'm going to move faster. These are just results. So the main part, I think we discussed it. But this is injection production as a point load. And, you know, point load is quite challenging with pins because everything has to be kind of a distributed function. So we use this delta representation to kind of smoothly apply this. But the problem, the boundary conditions are as this, and you are injecting and producing with a sinusoidal rate. And this is the analytical result. So there is an analytical solution to it. And using the sequential training, simultaneous training, we cannot converge. This was shown also by Beckler earlier, but using simultaneous training, we can at least converge. So the displacement results are accurate. We have, and this is time dependent, right? So time 0, 1.5, and this. So as we are going again, we run into this numerical diffusion that we were discussing for earlier stage. But all the conditions are satisfied, but then as you move forward and forward in time, the numerical diffusion comes in, and we lose a little bit of accuracy there. The most interesting part for this was in the inverse setup. So inverse setup, the same problem. We only use now 6 sensors. These are, by the way, collocation points. So more collocations around this injection production because of the type of function it has. But sensors that we are reading displacement and pressure. So very reasonable, not a dense network of sensors or anything like that, only 6 sensors total. So this is the solution that we obtain, almost as accurate. It's better represented here. So at the important points, it's like right on top of each other. Of course, if we show the absolute error, it's within 5% or so. But on the inverse side, so it's more interesting because it shows the sequential process. Every vertical line is a sequential training, is a operator split training. So we first solve the first solve, you get the kind of permeability and drain under or overestimated, but then the second solve correctly, and then third solve and fourth solve, you're almost to the right location. Another problem among these coupled problems we looked at was non-isothermal injection production flow in a rigid domain. So the formation is rigid now, but coupling between temperature and pore pressure. And this was also a very challenging problem to kind of obtain without imposing any symmetry or anything, to obtain these smooth results and to see the temperature distribution and also pressure diffusion over time. And these are the results compared to finite element, again, for very long times. And the last result that I want to present today is now we have thermoelastic consolidation. So you have multiphase flow, saturation is around 0.5, multiphase infiltration. So you have some increasing humidity or some rainfall from top, and it infiltrates to the system also with increased temperature. So this is also a very challenging, kind of common problem to validate classical numerical solvers. And we solved it both for forward and inverse. Again, for the inverse is really interesting because only 3 sensors. This is, by the way, very similar to some experimental setups that people use to kind of characterize soil or rock. And only with 3 sensors, PINN regression can capture the solution space very nicely. And also in the inversion, now we added one more parameter, and it would capture the parameters also very accurately. Our objective, ultimate objective, is really to go to real scale, to engineering applications. This is a work by one of Ruben's students back in 2015, which they used INSAR data and well pressure to kind of characterize the system. And it was challenging at the time. It is still challenging today, and our hope is to address such a problem someday. With that, thank you very much for the opportunity to present this work, and thanks the audience for attending this talk. And yeah, I would be happy to take any questions.
Ehsan, do you have your papers somewhere, a reference, like the splitting operator, the operator on splitting? Which paper was that?
I just realized I haven't cited any of them here, but I can send you. So the inverse part, we just submitted to JCP, but then the other 2 are already published. One of them, they were forward solved using PINN. One of them is at CMAME. I can send you the main one.
So the first splitting operator, because I would like to reference you. The first splitting operator is in SMAME?
Yes.
Okay.
Thanks.
Thank you, Ehsan. Do we have questions for the speaker?
I have a question. This is Eric Sear at Sandia. So in the splitting approach, it's failing. Well, I mean, the classically an operator split scheme will fail because things are strongly coupled in a bidirectional direction. And it seems like your choice of splitting, the sequence you choose, is probably very important in this context. Have you considered things like transfer learning to kind of accelerate training of kind of later time variables?
Yeah, for example, that heat transfer, we actually had to use transfer learning because the region that we are imposing the injection production is quite small. So transfer learning, not kind of taking data from finite element. Our objective was to see how much we can do with PINN for the context of porous media. So instead of having a very small injection production region, we first started with a kind of larger one to have a more faster convergence, and then gradually reduced it to the target value. But really, in the classical methods, there are a lot of works classically, like this one by Kim, who is now, I think, a professor at Austin, on which approaches for operator split are stable and which are not stable
But
in the context of finite element.
So, I mean, I guess I'm curious though, if you basically can build your architecture so that, you know, in a sense, when you have a stable operator split scheme, it usually means that the variables depend on each other in kind of like a triangular way. So you can go from the initial one, which is fully decoupled, and then you have information propagating through each variable. I could imagine taking your neural network and then using, say, like a headless version of the temperature network in the next kind of solve, and that might in fact accelerate the, say, the strain or stress. So slightly modifying your architecture so it looks like basically the temperature network feeds into the strain network.
I think we are using a similar strategy, right, with sequential training. So you solve one of the equations and you don't actually need to go extremely accurate on the first iteration, and just to get to some average reasonable numbers that satisfy those boundary conditions. And then you would pass that information to, for example, solid solver or to fluid solver back and forth. But if you mean at the end, we do like a full solve, we found that full solve decreases the accuracy of results. But I think a domain decomposition approach would be much more helpful, especially in time, because with time, you can transfer the weight essentially. So you can just solve for, I don't know, 1 time second, make sure that is satisfied, and then just save the weight at that state and go to the next time, and save the weight and go to the next time. And this way, by the end of solving, you have a set of weights that belongs to each time domain. And I think that is something possible and very reasonable to do.
Okay, thank you.
Thanks.
Yeah, we do something very similar with Navier-Stokes, for example, for training for flow past the cylinder in the unsteady case. Otherwise, it's very difficult to. People have pointed out that, but now we know how to do that. That's why we call that sequential. The other one, what you could do is, but just for people.
I thought you called that parareal.
No, well, I'll try to avoid that. But
Okay.
But the N here is your iteration, right? And if it's you do mini batch, that's the epoch number, like you were showing.
That's the, yeah, epoch number, but each epoch has, depending on the sample size, a few hundred mini batches. Yes.
Yeah, sure.
There is a question from Simin. Simin, you can ask the question directly.
Yeah, Simin is the one who is doing splitting. So. Yeah.
Hi, hi. I am Simin from Brown. Thanks for your nice presentation.
Thank you.
Excuse me, could you show the slide 50? I have some questions.
Okay. Yeah.
Okay, right. What was your domain for solving this problem? Is 0 to 30?
Domain, you mean the domain size?
No, the domain. I mean the interval for solving problem.
Time interval. This
Yes.
is maximum. I think is at 75 days. So the from 0 to 75.
So you have one step for solving problem by splitting, right?
But not splitting in time, right? Splitting in the optimization. So first solve temperature, then solve pressure, and pass the information back and forth.
Right.
Yes, but as I know, when we want to solve problem with splitting, we should also solve problem in sub-intervals, right?
If you're reducing the time domain, yes, I suppose.
And the error is depend on the step size.
I can imagine. Yeah, we didn't test it on this problem. We spent a lot of time on Mandel. For Mandel, it was clear. As soon as you reduce the time size, you increase the accuracy over time.
Right. Right.
I suppose it happens similarly here.
And do you check the order of error with the splitting? I mean the order with respect to a step size.
So we don't have a step size, right? These are just the times for outputs. So just
you have your
just,
step is whole domain.
Exactly. A step is just one step, 75 days.
Okay, thank you. And another question.
Simin is different. What you're doing is different than what Ehsan is doing.
Yes, Ehsan has solved her problem in whole domain. But for me, because the domain is bigger, when we consider just one step, the accuracy is decreased. Because the order of error in splitting, in re-splitting is 1.
Because you're looking at transient. That's why I pointed out before that also his pressure is a transient pressure is, but then the steady state is good.
Right. And also I have another question. You said you freeze parameters, right?
Yeah.
I want to know, did you compare your results without freezing that or not?
Yeah, we did compare, and the freezing is much more accurate, which makes sense, especially for so with the operator split, if you especially classical methods, it's always freezing, right? So you solve for displacement, and the displacement is fixed. So you don't solve it until you solve for pressure and other variables in the system.
Yes, the solution of each sub-problem should go to the next problem. And also the values of parameters will go to the next sub-problems, right?
Yeah.
Okay, thank you.
Yeah, of course, thanks.
Ehsan, did you try to, like one of the problems we had in the original paper with Majar was the Kuramoto-Zhivazinski equation. We couldn't solve it in forward problem. Even the Alan Kahn we could, but let's say Kuramoto-Zhivazinski, because it's like a dynamical systems, it develops transitions to more chaotic systems. Did you try your approach for that to see if you can, even with the smaller time steps, if that works there?
No. I'm not familiar with that equation, but our focus was in the beginning was from THM processes, but then because it didn't work, we first said, okay, let's first solve the solid part and see how it works. And then gradually adaptive weights came in and other sampling papers and so on. And gradually we also made some changes, and we got to this back. Actually, I think you had a presentation in 2018, and then Maziar had a presentation later on when the paper was archived, and Ruben and I was lucky to attend it and immediately start working on it. So, but we never solved that problem. So,
yeah, that's that in space. Yeah. Anyway, it's a transition. It's a flame. It represents a flame that goes laminar to turbulent, basically. It's simple. It's XT, one in space and time, but in the temporal
we
behavior.
Can try it. Yeah, I think I will check it out later after this talk. Yes.
So just a quick question. When you do the splitting, you said that you freeze it, but are you using a single optimizer for all of the variables? So like if you have momentum or something, is it one momentum variable that's shared across all fields? Or would you set up like a different atom optimizer, for example, for each field? Just in terms of the linear algebra, right? Like if you were to solve a monolithic multi-physics system, right? You would never throw gradient descent at this, right? Like each field would have a different condition number and so on. And
that's a good point. Yes, we actually set up 3 optimizers. We can set up just 1 optimizer because naturally the derivative of loss, if you just use loss of temperature with respect to others, would be 0, but it's just computationally inefficient because if it's just 1 optimizer that tries to take the derivative with respect to all parameters, it just evaluates it as 0. So we set up 3 optimizers in this case so that it's more efficient, but we didn't need to do that other than the efficiency. But yeah, that's a
No, but that could be the key actually, Ehsan. This could be the key. The fact
Exactly,
that you
yeah.
have a smaller landscape, and that's really. I mean, this your results are amenable to a lot of interpretation and analysis. So thanks for sharing it. But my guess is that you're benefiting from that, from a smaller landscape.
It's a little bit counterintuitive. You wouldn't expect that doing splitting would make it converge faster. So you must be getting something somewhere, right? So that could be one
The
place where you have
optimization.
adaptivity in the learning rate.
Yeah.
And so it makes it in the sense that you have like so many losses, right? So we have many terms. We have Newman boundary and Dirichlet boundary conditions and the PD loss itself. And then when you add all of this together, so you end up having like 20, 30 losses. And even if we use like adaptive weight, now it's really a mess in the loss landscape. Like it's could be highly non-convex and so on. It's extremely challenging. In fact, it's difficult to visualize it. There are some proposals to, I don't know, take a norm of the parameters and then, but that norm that you take when you have all of these losses together, every direction that you look, the loss landscape is different. So there is no way to make like a proper conclusion whether which regime we are operating. I agree with your point. I mean, it makes it a smaller too. But I think theoretically, because gradient of loss T it only relies on network T, right? Loss T, the gradient with respect to theta U or theta P should be 0. And when we experiment, it's also 0. But whether algorithmically this just 0 values causes some trouble for Adam optimizer in terms of picking its internal variables more accurately or less accurately, I suppose, yes, there are a lot of looking at averages and so on. So if lots of zeros come into averages, then there might affect some of the hyperparameters of Adam optimizer.
You could design these are on one hand very impressive, right? Examples because of their complexity, but you could design a much more simplified problem with 2 time scales to it, right? Maybe just like a 1D plane wave problem, right? Where you could actually identify the dependence on that condition number, and you could look at like whether one of them is picking them up. You know what I mean? So it'd be really interesting to understand what the mechanism is here that's making the magic happen.
Yeah, so I think one way is to, as I said, we had it in our to-do list, but never got to it. But in fact, in Cyan, I already have the functionality to evaluate the NTK on any grid that you pass in. And if we evaluate the NTK matrix, right, and we take a look at eigenvalue spectrum, it certainly gives us some perspective why one of them works better than the other.
Exactly, like a 1.5D, like a normal mode stability analysis based off the NTK might give you that. Anyway, excellent talk. Thank you.
Yeah, thanks. Great point.
Thank you, Ehsan. Yeah, George, please go ahead.
Yeah, I just want to thank Ehsan because this provokes some more thinking for everyone, and it's very timely because we just got also good results for our dynamical systems using splitting operators, and so that's excellent. We have also serious business to do. We have a barbecue to attend now, so we'll have to maybe wrap it up here. And not too bad you are too far away, but We'll drink one for you.
Next time.
Thank you very much. Yeah, I will make sure to have a hamburger here too. Thank you very much. It was a pleasure.
Thank you everyone for tuning in, and to all the Crunch members, let's meet at the Crunch barbecue, and to all others, have a great rest of the day. Thank you.
Thanks. Bye now.
Bye.